Welcome, everyone. We will start now with the Post-Quantum 2 hardware session. And the first talk is optimized hardware software co-design for Kyber and dilithium on RISC-V system on chip, FPGAs. And the talk is given by Tongfei Wang.
Thank you. Good afternoon, everyone. I'm Tengfei from Shanghai Jiaotong University in China. I'm very glad to give a presentation about our paper on behalf of all the co-authors. The title of our paper is Optimized Hardware-Software Co-Design for Kyber and dilithium on RISC-V SoC FPGA. My presentation includes 5 parts. First, I'd like to introduce the design rationale as well as some background. Our research focuses on Kyber and dilithium. They are both modular lattice-based post-quantum cryptography. In the newly released Pqc standards, FIPS 203 is derived from Kyber. FIPS 204 is derived from dilithium. A common security assumption of them is the hardness of the model learning with errors problem. In simple terms, the MLWE problem can be described as follows. Given A and A times S1 plus S2, where A is a matrix with elements in a polynomial ring. S1 and S2 are polynomial vectors with short coefficients. There is no efficient algorithm to determine S1 and S2. From an implementation perspective, A times S1 plus S2 is the major operation for both Kyber and dilithium. Here we list the major parameters and operations for Kyber. The operations are divided into polynomial arithmetic operations and other operations. We tested the performance of software implementation on our selected platform. The result is shown in this figure. It can be seen that the polynomial arithmetic operations account for 40 to 50%. For dilithium, we run a similar test. The results show that the polynomial arithmetic operations also account for a high proportion. Based on this observation, we decided to design a hardware accelerator to speed up the polynomial arithmetic operations. The other operations, such as short-range summing, can be optimized through software. We aim to achieve a balance between performance and cost. The implementation platform we selected is the industry's first RISC-V-based SoC FPGA platform, named Polyfile. RISC-V is an emergent processor architecture. Previous RISC-V-based work usually uses an open source software core and make some modifications to it. We would like to run Pqc on RISC-V hardcores with standard ISA. Besides, this platform combines RISC-V processors with FPGA in a single device. We can use the FPGA to evaluate our hardware design. This page shows our system design on such a RISC-V SoC FPGA platform. It's a hardware-software co-design that includes hardware acceleration and software optimization. For hardware acceleration, a loosely coupled accelerator is designed and implemented on FPGA. It performs polynomial arithmetic operations. We take efforts to make it high performance and cost effective. The flexibility and countermeasures are also our concerns. The software optimization involves 3 aspects. Firstly, the first is collaboration with hardware to accomplish polynomial matrix and vector operations. The second is optimizing SHA-3 functions on RISC-V processor. The third is using multiple cores to speed up the other functions. Next, I will introduce the detailed design for the hardware and the software. The second part is hardware acceleration. I will describe our hardware design from the bottom up. For the modular multiplayers, we present dedicated designs for Kyber and DLSM respectively, based on the features of their moduli. The modulars in Kyber can be represented as sum of powers of 2. In the Montgomery reduction algorithm, it needs to pre-compute W equals the inverse of Q mod R. When R is set to 2 to the 12th power, W can also be represented as sum of powers of 2. Therefore, we can replace the multiplications in Montgomery reduction algorithm with shift and addition operations. Below is the hardware block diagram. It takes only 3 clock cycles to calculate a modular multiplication. For DLSM, we use a different way. We take advantage of the congruence relation between 2 to the 23rd power and 2 to the 13th power minus 1 on modulus of Q. Although this principle has been exploited by previous work, we modify the intermediate process to make it suitable for 18 times 18-bit math blocks provided by Polyfile FPGA. The dedicated modular multiplication is summarized as algorithm 2. The corresponding hardware block diagram is shown here. It also takes only 3 clock cycles to calculate a modular multiplication. Based on the dedicated modular multipliers, we present a highly efficient implementation for number theoretic transform. NTT as well as inverse NTT is the key operation for both Kyber and DLSM. In our design, NTT is calculated by CT butterfly, and INTT is by GS butterfly. This figure shows the data path for the butterfly units. They both have a 4-stage pipeline structure. In practice, the hardware resources are reused. For the whole procedure of NTT, we instantiate 4 butterfly units in parallel. The conflict-free memory mapping scheme proposed in CHES 2022 is applied. 2 consecutive coefficients are stored in a single address. This is a common structure for both Kyber and DLSM. Despite that, the last layer is omitted for Kyber. The polynomial multiplications in entity domain for Kyber and DLSM are different. For Kyber, we adopt Kashuba method to calculate the polynomial multiplication, as shown in this formula. The benefit is that it only needs 4 modular multiplications for each group. Therefore, the hardware resources can be fully reused. As shown on the left of this figure, the data path for Kyber is divided into 7 pipeline stages. The right is the path for DLSM. It follows a pointwise manner with 4 modular multipliers in parallel. Now we can see the high-level architecture of the hardware accelerator. It consists of several components. The polynomial arithmetic unit is responsible for executing polynomial arithmetic operations. As mentioned above, it can be configured for various functions, such as NTT, INTT, multiplication in entity domain. we use 3 4-bank RAMs to store the polynomials. RAM 0 and RAM 1 each stores a single polynomial using conflict-free memory mapping. RAM 2 stores a polynomial vector, which is initialized as zeros. The ADDR-GEN generates addresses for the RAMs, whether in place or shuffling. A finite state machine controls the operation sequence. It receives the configuration information from the conf reg. This accelerator can interact with a processor through the ASI4 interface. The FSM is carefully designed for Kyber and DLSM. This page shows the functions and transitions for transitions of different states. The state transition is corresponding to the actual requirement of the algorithm. For example, the key generation in Kyber needs to transform S into entity domain. The corresponding path is idle, write 0, entity 0, MACC idle. The advantage of the FSM is avoiding unnecessary data transfer between hardware and software. Therefore, the software only needs to send a few instructions to complete complex computations. The third part is software optimization. Data transfer between hardware and software can be time-consuming. To mitigate this disadvantage, we employ the direct memory access technology. DMA engine builds the direct channels between memory and the FPG. As you can see from this code, the processor only needs to specify the source and destination addresses and the number of bytes to transfer for one channel. Then it waits until the transfer completes. The below figures shows the effects of DMA. Compared to processor transmission, the clock cycles are significantly reduced using DMA. Besides, the scratch pad configuration of L2 catch can further reduce the cycles. The polynomial matrix and the vector operations are implemented in a way of hardware and software collaboration. Since the accelerator does not provide large RAMs for the polynomial matrix, it requires a reasonable schedule for the software to calculate these operations. The schedule should avoid repetitive data transfer and calculations, keep all intermediate results in hardware, only read the final results. It should have a good collaboration with the hardware FSM. For example, when it computes A times S1 plus S2, the process can be described as algorithm 4 and this figure. The vector S2 is firstly written to RAM2. Then write one polynomial in A to RAM0, one polynomial in S1 to RAM1. The polynomial multiplication can be executed under the control of FSM. This result is then added to RAM2. Then RAM1 maintains its value. The next polynomial at the same column of A is written to RAM0. In this order, it can ensure that no repetitive data transfer and calculation exists. At last, RAM2 stores the final results, which can be read by the software. Besides, the arithmetic masking countermeasure can be easily applied. It is reflected by the outer loop. For SHA-3 functions, we do not use hardware to accelerate it. Instead, we use Fluting, we use RISC-V assembly instructions. Previous work proposed the idea that using floating registers to store the state array. In this work, several further optimizations are proposed. Firstly, memory access in the intermediate process is fully eliminated. Secondly, the execution order of assembly statement is carefully arranged. Thirdly, RISC-V standard compressed instruction set extension is used. Take the theta step as an example. It computes the parity for each column. The left is the original code. In the right frame, there is a heavy data dependency between adjacent instructions. It causes a bad impact for the pipeline performance. After optimization, this dependency is eliminated, and the compressed instruction is used to reduce the code. The optimization for the other steps follows a similar way. The other operations, such as sampling, packing, encoding, are suitable for parallel computation on multiple cores. Each core deals with several polynomials from matrices or vectors. The multiple cores synchronize through interruption, communicate through shared memory. Take the matrix expanding function as an example. The task is assigned to 4 cores. Each core samples 4 polynomials. The first core reads interruption signals for the other cores. In idle conditions, the parallel computing can reduce the time by 3/4. Now let's see the experimental results. This table shows the resources and the clock cycles of the hardware accelerator. The resources are measured by the utilized components provided by the polyfile FPG, which account for less than 5% of the total. The clock cycles reflect the performance of parallel and fully pipelined computing. They are in line with expectations. Besides, the shuffling countermeasure has little impact on resources and performance. The comparison of these two figures demonstrates the effects of hardware acceleration. Obviously, the clock cycles consumed by polynomial arithmetic operations are reduced significantly. It reduced by 70 to 90%. As a result, the overall performance improves by 20 to 50%. This page shows the effects of code optimization for SHA-3. We evaluate the functions individually. The performance improves by 15 to 20%, and the code size decreases by 40 to 60%. In this page, we show different implementations of Kyber and DLSM on its security level of 5. It can be seen that on top of the hardware acceleration and code optimization, the multi-core acceleration further enhances the performance by 40 to 60%. Compared with baseline implementations, the overall performance can be improved by 60 to 90%, 80%. We can compare with the related work. This table shows the different implementations. Compared with reference 2, 3, and 5, our accelerated implementations perform better. The reference 4 gives the best performance, but it also uses much more resources, and it resembles a pure hardware implementation. The comparison of DLSM 5 is similar, especially the reference 7 implemented their design on ARM-based Zinc platform. The third version of our implementation performs better than them. This table shows the comparison of FPG resources. As previous work, all use Xilinx FPG. We resynthesize our hardware accelerator based on Xilinx FPG using Vivado. The results show that our accelerator consume less resources than the others, except for reference 2. But reference 2 also gives the worst performance. In addition, we conduct a side channel leakage evaluation experiment. This is a runtime power consumption trace. There are two obvious patterns corresponding to NTT0 and MACC. We use TVLA method to evaluate the power leakage. This page shows that obvious power leakages exist if the accelerator is not protected, while the countermeasures we take can mitigate these leakages. At the last, we give some conclusion. This work presents an optimized hardware-software co-design for Kyber and DLSM. We design hardware accelerator for polynomial arithmetic operations and optimize the software code for SHA-2 and other operations. It improves the performance by 3 to 5 times at a cost of less than 5% of the total FPG resources. The source code is available at GitHub. Welcome to visit. These are the major references. That's all. Thank you for your attention.
Thank you very much for your talk. Are there any questions? Okay, then I have a quick question on slide 27 with the comparison. When you compared your results to the previous results, you mentioned that you optimized for area, so to decrease the area, to be more flexible. Can you improve the speed and the performance by using the free area in your design when it's not needed by a different process?
You mean I use free area to increase the performance?
Yes, because you did not use a lot of DSPs or BRAMs, and so can you just, for example, multiply your design, or are there drawbacks by using the RISC and the DMA?
Okay, thank you for your question. Generally speaking, the performance is usually improved with the cost of resources. Our design try to use less resources to speed up the computation. We try our best to make the calculation more efficient, but it's using free resources is hard to implement. The software, on the other side, the software implementation can, for example, the SHA-2 optimization uses no actual hardware. The performance is also increased. Yeah, thank you.
Okay, thank you very much. Let's thank Tang-Fei Wang again.
Thank you.
So the second talk will be an online talk. It will be given by Juxiao Liu. Well, it's a video, and we have the speaker in the chat. So if there are any questions, feel free to ask, and I will relay the answer.
Hello, everyone. My name is Guoxiao Liu. I'm going to give a talk about the high-performance hardware implementation of MPC Head and Picnic 3. This was joint work with Ke Tingjia from Tsinghua University and Wu Wenwei Leiju from Shandong University. In this talk, I will be first going over the background of ampicillin hide and picnic. So what is ampicillin hide and how does it work? Then we are going to be exploring the hardware implementation of ampicillin hide with pre-processing. Finally, I will be showing you the picnic by use pipeline and give the results. With the famous Shor's algorithm and Grover's algorithm, quantum computers have increasingly impacted classical cryptography. The US NIST has begun circulating post-quantum cryptography algorithms, and Picnic is one of the third-round signature candidates. Unfortunately, Picnic did not ultimately won. However, Delicium Falcon and Phoenix Plus family won the competition. However, currently NIST have started a new round of algorithm solicitations. Many digital signatures based on Amazon Hide and its variants have been proposed. We will mainly introduce Picnic, the first digital signature algorithm based on Amazon Hide. The security assumption of Picnic is based on symmetric primitives, especially the security of one plain text and ciphertext pair in OMC. It's worth mentioning that in the new round of digital signature submissions, 9 out of 40 are based on MCC in the hide and its variants, such as FACE, SDITH, and so on. MPC in the hide was proposed by Ishai et al. Using MPC protocols to construct zero-knowledge proof. Gicomley et al. Used symmetric ciphers as one-way functions and construct the zk protocol using MPC in the head. Chase optimized the zk protocol and designed the Picnic digital signature, which later became known as Picnic 1. Katz and all construct the magnetic hide with pre-processing, reducing the size of zero-knowledge proofs, which lead to the KKW protocol and the signature Picnic 2. Kells et al. Implemented Picnic 1 on FPGA, and they proposed the Picnic 2 is hard to implement. And then Kells optimized the KKW protocol and proposed the Picnic 3. Okay, next we will briefly review MPC in the hide. The term in the hide referred to the prober simulating n parties executing an MPC protocol to compute Gxw1 to Wn equals Fxw, where W is the XOR of the secret witness Wi held by each party Pi. Similar to the classical Sigma protocol, the prober commits to each party's will and send this commitment to the verifier. The verifier chose a challenge and the prober opens the commitment. The KKW protocol is divided into two phases, the offline phase and the online phase. The offline phase involves the computation of masks lambda, and there is no witness used. While the online phase computes the masked witness, the prober simulates n parties and each one holds is shear lambda alpha I. The secret witness is Z alpha, and the mask is lambda alpha. The mask width is Z alpha height equals Z alpha XOR with lambda alpha. During the offline phase, each party samples a shear lambda alpha for the input wires of the circuit and samples a lambda gamma for the output wire of each AND gate. Additionally, a shear lambda alpha beta is sampled for each AND gate where alpha, beta are the input wires and gamma is the output wire of AND gates. For XOR gates, each party computes locally. Where for AND gates, n parties jointly compute lambda alpha beta n, which equals lambda alpha times lambda beta XOR with the sum of lambda alpha beta 1 to lambda alpha beta n minus 1. In the online phase, each party still computes XOR gates locally, but for AND gates, Pi computes Si locally and then jointly computes S to obtain the gamma height. Okay, we have briefly reviewed the amplitude height of its pre-processing. Our main contribution is that we show at the gate level that the hardware optimization of amplitude height with pre-processing is influenced by the number of parties only for nonlinear operations, not for linear operations. Therefore, even when the number of parties is large, it's possible to implement it on resource-constrained FPGAs. For example, our experiments have shown that low MC with 16 parties can be implemented, and this optimization is significant for low MC, where the cost of the linear layer is substantial. We also provided a pipeline implementation of Pqc 3, which we believe can be applied to other digital signatures with using a similar pipeline approach. Next, we introduce our circuit model. Similar to the left figure, the round function of low MC, our circuit model consists of layers and layers where A is a nonlinear line and X is a linear line. Next, let's see how the optimizations by KZ20 in the circuit. This optimization has been applied in many MPC protocols, which involves swapping the order of shear computations and XOR gate computations. In the original protocol, each party used their shears to compute XOR gate locally and then jointly compute the XOR of the shears. Since both operations are linear and can be swapped, it's possible to first jointly compute the XOR of the shears and then compute the XOR gate. Therefore, for XOR gates, we do not need the N gates, we just need one XOR gate. Okay, as you can see, through this optimization, the linear layer requires only one gate instead of N. And since the linear layer in low MC occupies a significant amount of resources, this will significantly reduce the hardware usage. Of course, for the online phase, this optimization cannot be applied directly and requires more complex operations. We will not go into the details, but after this optimizations, the online phase can also use only one XOR gate instead of n XOR gate. Okay. Before showing the results of low MC MPC, we first give an optimization of the clock cycles for low MC MPC. In the offline phase, we need to compute Ki and also compute the linear line inverse for the state. Since the calculation of the linear inverse requires Ki, this will consume at least 2 clock cycles. However, in the online phase, we calculate the secret Ki and the state, which only takes R cycles because the calculation of Ki and the state can be done in parallel. Our optimization is straightforward. We can combine the two linear operations as shown in the formula in this slide, which does not increase the critical path but reduces the clock cycles to R. However, this will lead to an additional matrix K prime, which increases hardware resources. Here are our experiment results for low MC MPC. As you can see, as the number of parties increase, the increase in resource usage is not significant. The hardware usage for low MC MPC with 16 parties is less than twice that of 3 parties. And our implementation requires fewer resources than the hardware implementation of low MPC in Picnic 1. Next, we briefly describe the process of digital signature generation. We divide Picnic into 3 steps. The first step is constructing the Merkle tree for each instance. The second step is divided into 5 parties for an instance, generating random seeds and random types, low MC MPC, commit to the state and commit to the offline and online views. The third step is a hash function to reduce the communication between the prover and the verifier. We implemented a 4-party Picnic. To achieve high performance, a lot of parallel computation is required, especially for hash function calculations. To achieve high performance, the number of Pqc instances is more than twice that of n, which has become a limited factor for Picnic's hardware implementation. The hardware resource for Picnic 3 are now constrained by Pqc rather than low MC. This is our overall architecture. First is step 1, followed by the pipeline design of step 2. Since step 2 involves an instance, MPC in the head or with it is repeated sign processing is very suitable for pipeline. And then finally, we have the step 3 to hash. The performance of the pipeline depends on the worst part. We consider the symmetric primitives we use, testing Pqc running 1 round, 2 round, 3 round, 4 round, and 6 round per clock cycle. The critical parts of low MC is much larger than that one round of Pqc. So to improve the pipeline's performance, we use a Pqc with a critical little lower than the low MC MPC. Okay, thus we implemented several versions of Picnic 3. These are our implementation results. From these results, the version using Pqc 3 performs only slightly better than the Pqc 2, but consumes significantly more hardware as the critical path increases, and there are additional because there are additional control logic cycles. The optimizations is not apparent in this case. So we suggest the Pqc 2 version. Okay, next is a hardware implementation with other signatures as a L1 security level. The every time product of Picnic 3 has a significant advantage compared to other digital signatures. Also, as a L5 security level, it still had a advantage over Phoenix Plus, which is based on symmetric primitive assumptions. Okay, that's the reference. When we first started the hardware implementation of Picnic, there were few MPC in the high digital signature accessible. However, by the time we start our presentation, Picnic is slightly out of date, and many new protocols and signatures have been designed. From our paper, it appears that MPC in the height is highly suitable for constructing pipelines, and therefore we hope to contribute to the hardware implementation of MPC in the height in the future. That's all. Thank you.
Okay, thank you very much. Are there any questions? If so, please step to the microphone. Okay, I will try to ask a question and let's see if it works because the speaker is not able to get the audio into this room. So my question would be, on the slide 23, there was the comparison with other algorithms, and the other algorithms like lithium, they used DSPs to reduce the amount of LUTs and flip-flops to reduce the area. Is this also possible in this design? Because there was no hardcore used. Let's see if it works. And if not, you will have a longer track switch break. So if you heard the question, can you please write something in the Zoom chat? Okay, it doesn't appear to be that way. So let's thank both speakers again.